Process. Joe released the first version on the Scottish Government website of the carbon impacts on peat calculator. So we rapidly altered the way we constructed ours so that they could talk to one another. We approached Joe, Scottish Government and Forestry Commission funders. They allowed us to do a little bit of work to demonstrate that the integration of the two approaches was possible, and now we're at the point where Scottish Government has asked us to progress that to a certain point. I'm going to talk to you about the forest management bits. Barry will talk to you about the forest-tree-wind interaction bits. If we have time at the end, I'll say a little bit about the statutory planning and forest strategy impacts as well. So the project's aim is to model and quantify the impact of a range of forest management alternatives on the carbon balance of wind farm projects which were within and or adjacent to existing forestry. I don't really need to go. So within the Climate Change Scotland Act, there is very strong incentives for the development of renewable energy technologies, one of which is wind. But there's also very strong assumptions regarding the net benefits to society of carbon capture by forests. Forests are very efficient solar panels, if you want. They convert solar energy into timber, and they're very good at it. So we have to take that as a fundamental understanding that the forest is actually providing a very useful service to society. And public bodies such as Forestry Commission, Scottish Government, have a duty to help deliver emissions reductions targets, maintain the land use capability, ability to adapt to future climate change, and do that in the most sustainable manner. That's why there's regulation, planning, etc., etc. Now, the original calculator that Joe put together, I'm sure most of you in the audience have seen this, looked at the annual emissions savings offset against carbon-intensive fuel sources for a site with a given capacity factor. It looked at all of the various processes that you have to account for in that LCA style analysis. In looking at the forestry impacts in the existing version, the version you can download off the Scottish Government website, forest carbon loss is calculated at a fixed rate that's integrated across the rotation life of a forest. The standing forest carbon is unaccounted for. Where does it go when you fell it? There's a loss of it to the atmosphere, but what you do with the actual timber product is not within the boundaries of the calculator as delivered. There is no impact of that forest being adjacent to the turbines. It only does deep peats, and forestry, there is quite a lot of forestry on deep peats in Highland Scotland, in very windy places, but there's also a lot of forestry on organomineral soils, which are becoming an increasing focus of the developers' portfolio. There was no operational impacts and operational variation. By that I mean the ability to manage the forest. So, in the new version, forest carbon loss varies with age. It is explicit. So if you fell a 25-year forest, you lose the CO2 in the timber in that 25-year-old forest. You have the opportunity to capture some net benefit for the development by burning it as a non-fossil fuel, as a low carbon energy source. Wood fuel. You can use it as wood fuel. charged for the net carbon loss over the duration of the wind, of the site's lifetime. So if it's a 25-year proposal and you've chopped down trees at 25 years of age, you have then, in a normal situation in the UK, 25 years of highly productive forest carbon sequestration that is a debit on your account. And we model this using a very bit simple but process-driven model called 3PG. And it's been decoupled, I'll say a little bit more about it, it's been decoupled to be fairly simply applied across Scotland. We've extended the soil types primarily because not all forests grow on peat. And we've included the operational impacts, the cost of felling of trees, in terms of the fuel usage, etc. And we have included options for experimenting with operational management variation of that forest. And so I'll touch on 3PG. 3PG is driven by climate, temperature, rainfall, etc. It then has, essentially it assumes a tree is a huge leaf, and it partitions the carbon that's captured by that leaf into a growing tree, and some of that is put into stems, some of it into the ground, some of it turned over in roots, but it's a fairly simple process. It's bread and butter for a physiologist. This is the actual program that we use to run it, and you can see it's a little bit more involved, particularly in the soil component. My colleague Georgios Sinakis, who's at Edinburgh University, is responsible for this part of the project. And what we're doing is we're using a complex physiological model which we then simplify down into the most essential elements to give you a reasonable estimate of the carbon exchange that the forest provides. Thanks to Joe for these diagrams. They're not all working. So what's the total net carbon benefit? Well, there's something gone a little bit strange here. It's a version control. I work for the civil service. We only have PowerPoint 2003. Net benefit, net turbines, potential biomass, minus site CO2 losses. If we remove all the trees, we get a very predictable wind profile, and we maximise the potential net benefit from the turbines. When a forest is present, its physical presence alters the wind turbine profile. This is the expertise of Barry, so I'm not really going to go there anymore. But the essential thing is it lowers the capacity factor. You're not going to get as much output from your turbines in the presence of forests. But we can manage those forests in a number of ways. We can take our harvester and create a keyhole. The tool allows you to set the keyhole dimensions as you see fit as part of your site management. And it's not fixed at 75 metres, it's just an example. You can take your harvester and you can fell. Oh, sorry, how did I go backwards? A large clearing. In this instance, I'm suggesting 250 metres. You can say it's 800. I really don't mind. Or you can fell the whole lot. In this instance, it's a 800 metres radius to the existing forest edge. But whilst you do that, you also have an option of then replanting a portion of the site with what I'm terming short rotation forestry. There's a number of means of managing forests to low vegetation height. Coppice is one of them. Coppice would be included under the generic forestry banner that I'm using today. Low height native woodland would be another one. We are not going to deliver you a tool that gives you all the different forest management options. It's going to give you an option of replanting with 1 of 2 species, but then managing their height. That's what it's going to do. If you want to do low density native woodland, you'll have to think up a clever way of doing that yourself, or come and speak to me privately and I'll agree a price. But what we can do is we can look at what happens with short rotation forestry. And we can look at how that short rotation forestry, whether we plant it out with a keyhole, whether we plant it within the large clearing, and all these options are there in the tool. So you can, it allows you to look at the different forest management options on then your total carbon emissions and carbon payback time. At which point I'll let Barry tell you about wind.
Okay, as Mike said, the presence of forests affects the wind profile. Is it that one too?
No, that one that's on the table.
Yeah, has this got a laser? No.
Yeah, we couldn't get it to work earlier. It wasn't working earlier.
Okay. The presence of forest affects the wind profile, and as we know from some wind farms that have been developed in Scotland, if you're not careful, the return from your wind farm can be quite severely impacted by the presence of those trees. Just a little bit of basic science about the atmosphere. The area closest to the surface of the Earth is called the turbulent boundary layer. It's quite turbulent, well mixed, up to about somewhere between 300 and 1,000 metres. That's why when you take off in an aircraft on a nice sunny day, it tends to be a little bit bouncy until you get up to a certain height. And you've got this logarithmic wind profile from the ground upwards, so quite quick increase in wind speed as you go up with height. But the shape of that profile depends on... sorry, I think there's a slide. There's a slide that's hidden there. Let me just check. I think that one's hidden. How do you unhide? It says hide, doesn't it? Okay, is that going to show up now? Okay, so over open country, you get to what's called a geostrophic wind speed. That's really the wind speed without constraint of the ground fairly quickly. Over forests, that's much slower. So at the same height above the ground over a forest, you'll have a lower wind speed than you will over open country. And it's even more dramatic in somewhere like the city, which is extremely aerodynamically rough. And people have done measurements on this where they've looked at, and this is a log plot here. So now our logarithmic profile looks like a straight line, open ground. And when you go from a smooth to a rough transition, as you move over that, the wind profile changes. So the wind speed is now going down closest to the ground, but at some height above the surface, you're back to the wind speed you had upwind. And the same happens when you go from rough, like a forest, to smooth, like grassland. And what happens is this profile, which is the red one here, starts to restore back. So the wind speed starts to recover. But notice it recovers from the ground upwards. Okay? This is all well known. It's been known for many, many years. Go back to German pioneers, Prandtl and von Karman. And this is just showing what happens over a forest. Wind coming from the left. Here's the forest. This is in a wind tunnel. And what you see is that inside the forest, a massive reduction in wind speed. But over the top of the forest, at this point, the wind speed here is 0.4 compared to what it was upwind. So the forest has a dramatic effect. It deaccelerates the wind speed quite dramatically. This is some work by Rodrigo et al. With a quite sophisticated computer model. Here you are in a gap. This is what the wind speed would be like upwind. And then inside the gap you can see that you've got very much a reduction in the wind speed. But the opposite of that is you get a huge increase in the turbulence intensity. So this is turbulence intensity. This is bad news for some a wind farm developer, because they've now got high turbulence levels at the base of this generator, and that could cause it to be damaged or cease to work. So what we did, and I don't want you to worry about the equations, but all I want you to know is they're relatively simple, these equations. You can be found in the standard literature, and you can code it up in a spreadsheet. That's why I use this tool. You don't need a complicated numerical model. You can just use what I call a roughness model to calculate how the wind profile changes to go from one type of land cover to another type. So you can take your logarithmic profile over open ground, over the open moorland, adjust it, it goes across the forest, adjust it again as it goes, say, over a gap in the forest, and then adjust it again as it goes over another bit of forest. And you can do that on and on and on, ad infinitum, and it's very quick. So you can go to that book and you can do it for yourself, if you wish. I've done it for you. And this is just to show, this is at Harwood Forest in the north of England. We had some measurements quite close to the ground, so up to about 15 metres, where we had a tower upwind of the forest and at different edges back from the forest. And the red here is a modelled profile, and the squares are what we measured. And then just under 4 tree heights into the forest, this is what I predicted with the model, and here's the measurements. And then 14.5 tree heights into the forest, here it is, it's green, and that's the modelled profile. And you can see exactly what I said. At the bottom, the wind speed starts to decrease very dramatically, but at some point it's the same as it was upwind, and as you go further and further into the forest, that height goes higher and higher. And this is the site. This is Harwood Forest. If people know that part of the world, it's near Otterburn, and we worked with they were called AMEC at that time. They had a 70-metre tower here in a clearing in the forest, and they put one out here. This isn't actually forest anymore, but they measured wind speeds there, and we were able to look at how the wind speed changed between this point and this point because of the presence of the forest. And so this is a logarithmic profile here, so the log profile becomes straight. So this is what I predicted for the model upwind, and here's the measurements from the AMEC 70-metre tower. And this is what I predicted inside the forest with the model, the red, and the purple is what the cup anemometers on the tower said. So it gave me reassurance that the model has done a good job of getting the wind speed profile correct. It doesn't do anything about turbulence. It's a very simple model, just looking at mean flow. Can't tell you anything about turbulence intensity. And this is just to show you what the impact of forest is on the energy yield. Here, assuming that the power output from the turbine is proportional to the wind speed cubed. So here we have tree height increasing. And then what I've done is I've compared the wind speed at different heights above the ground relative to a hub height of 100 metres. So with no trees, at hub height, obviously, the ratio is 1. Whereas at 50 metres, so halfway to the hub height, you've got a wind speed which is about 0.8283, so 83% of hub height. And as the tree height increases, you can see that all the wind speed ratios decrease relative to hub height upwind, and it begins to separate. So if you've got an 20-metre forest, then your hub height wind speed will be less than 60% of what it would have been out in the open. And so it's not wind speed, but this is a power output. But if you've got a turbine with a hub height of 100 metres over a 20-metre forest, you're going to produce less than 60% of the power that you would have got if you didn't have the forest. So you better take it into account if you want to calculate your payback periods. and get you get the bank to invest in you. One thing we don't have at the moment is we don't have any influence of terrain. And we know that's why we put things on hills in Scotland, because you get an increase in wind speed. This is just colleagues in France using the very latest large eddy simulation models to show that the wind speed profile is affected as you go over the hill. So you can see in the back of the hill you've got a very quiet area here, and at the top of the hill you've got a very sharp gradient in wind speed. This took 24 hours to run on a very sophisticated computer. It's not the kind of thing we can build into the spreadsheet. But it's possible to separate the effects of the forest, the roughness of the surface, from the effects of the terrain. So what you can do is you can take our simple roughness model and you can combine it with the outputs from a simple airflow model like WASP, and you can add those effects together. So that the wind speed, as an effect of hill and roughness, is the wind speed upwind plus, and this can be a negative or positive number, the perturbation due to the roughness plus the perturbation due to the hill. You can separate those effects. And I'm working with a colleague in Sweden who has been using the WASP airflow model and is using this roughness model and putting them together in a GIS, so that you can first calculate the effect of the terrain with no trees on it, calculate the effect of the trees independently, add them together. And then she's putting it all into GIS, and she's doing it to calculate the risk of wind damage, but equally easily you could do it to look at the effect in the wind farm. Okay, quickly summarising, because I'm sure everybody's very hungry. Wind speed is reduced and turbulence intensity increased over forests. And wind speed increases and turbulence decreases in gaps or behind the forest. Okay, stating the obvious. It's possible to model the wind speed changes across forests and gaps relatively easily, and we have that in the tool. And turbulence intensity would require more sophisticated numerical models. I've got some ideas how to do it more simply, but I haven't fully tested those at the moment, because I know that worries the industry a lot, and I'd like to include it, but I'm not promising anything. And current wind modelling does not account for topographic effects. So the tool we have here is just the effect of the forest. It's not putting the forest together with topographic effects. Potentially you could quite easily do something to say if your turbine was on the front of the hill, on the top of the hill, on the back of the hill, but we haven't promised to do that. The next step would be to link these results with the predictions of airflow models such as WASP, which I mentioned, and that's something I'm doing independently and separate from this project, but if I could somehow pull it in, I would do. Further testing is required against completed and planned wind farms. I mean, what would be wonderful is to get real data from wind farm developers where they've measured the kind of outputs they've got from their turbines after they put them up, and they've got wind speed data and they have power output data, because in the end the integrity of the tool will depend on how well it matches up against what people have experienced. And we need to continue, and I'm doing that. I mentioned Christina Blenau in Sweden and colleagues in France. Continue collaboration with other researchers to improve and validate the model and model assumptions. And what Joe said before is no model is ever finished. And I know researchers are often accused of saying, oh, we need to do more research. But the truth is, this is the best we can do at the moment. But next year we'll be able to do better because of the new information. Somebody will have done a key experiment somewhere that provides us a new set of data. Thank you very much.
Can you say that?
I'll just say that. Cheers, Terry. Which one?
Actually drawing them in the
Sometimes it's easier.
So within the planning process in Scotland, there's the drive for the development of renewable energy technologies, but there's also the drive for woodland expansion for a number of reasons, one of which is the carbon sequestration potential that forestry provides to society. The guiding principles embedded in that guidance and also now embedded in the National Planning Framework is for a strong presumption in favour for protecting woodland resources. Woodland removal should be allowed only where it achieves and demonstrates significantly and clearly defined additional public benefits. In appropriate cases, proposals for compensatory planting may form part of this balance or negotiation. So that's now in the National Planning Framework. What does that mean? Well, the first question is, can your proposal be achieved without the need for woodland removal? That doesn't mean that you can't manage the woodlands. It means that you can't permanently, the lifetime of your development, remove trees from the site. Can you do that? That's the first question. You might be adjacent, you might be within. Does the proposal have sufficient additional public benefit? Does the woodland require mitigation? How will the land use change? Well, here we go. Journal's strong presumption against. Where you have woodlands of national significance for biodiversity, landscape or historical and environmental reasons. Woodlands perceived to be critical to the provision of ecosystem services such as water quality, urban, peri-urban air quality, etc., etc. And if they're key in the delivery of forest habitat networks, this is corridors for bunnies and mink to gallop along in the landscape. They're key, they're key. Sorry, we're talking about mink on the way here today. Removal without compensation planting is possible if there's an enhancement of priority habitats that were within the forestry matrix. If there's specific species that are going to benefit from increased open land, again landscapes and historic environments, slopes, stability, public safety. Removal with compensatory planting is likely to be championed for developments within or adjacent to forestry, under a requirement for maximising climate change mitigation benefits, sustainable economic growth and improving the quality and extent of Scotland's woodland resource. So now that this legislation is embedded in the National Planning Framework, there is additional consideration to be had when you're thinking about how to manage woodlands adjacent to any land-based turbine development. That's all I've got to say.
Okay, so we were due to move on to Dali and the presentation of the actual carbon calculator before we go on to the hands-on session. Would it be better to have